Hi guys, welcome back to my channel. Today we are looking at scalar and vector quantities. Okay? Remember we said physical quantities are classified into three majorly: the fundamental and derived quantities, the dimensional and dimensionless quantities, which have been dealt with. Then here we have scalar and vector quantities. What are scalar quantities? Okay? Scalar quantities are those quantities that have magnitude only and without direction. They don't have anything to do with direction. So they are the quantities that are only described by their magnitude and unit of measure. For instance, now, let's say the mass of a body is 5 kilograms. The 5 is the magnitude, while the kilogram is the unit. So as far as the mass is concerned, nothing else can be used to describe it. Only the magnitude and the unit. So invariably, scalar quantities can only be described by their magnitude and direction. So what are the examples of scalar quantities now? Examples of scalar quantities, we have, for scalar quantities now, we have mass, we have distance, we have temperature, we have amount of substance, we have what again? Electric current. In fact, virtually all the fundamental quantities are scalar quantities. Okay? There is little controversy about luminous intensity. Luminous intensity is if another quantity. It should be a scalar quantity as well. There's some school of thought were saying it's a vector quantity, but to me, I would have said it's a scalar quantity as well. Luminous intensity, because it is only talking about the energy radiated by a source of light in a particular direction. That is luminous intensity. Only the light that's in a particular direction, not the quantity itself. So I can say luminous intensity is a scalar quantity. So all the fundamental quantities, invariably, they are scalar quantities. Okay? And if you look at this is a scalar quantity, distance is part of length. Then temperature, amount of substance, current, luminous intensity, what again? Fundamental quantities are 7 in number. 1, 2, 3, 4, 5, 6. It's remaining 1. And the last one is what? Time. So they are all scalar quantity as well. Okay? Other examples include electric potential. Electric potential is also a scalar quantity. Viscosity is a scalar quantity. Surface tension is a scalar quantity. Power is a scalar quantity. Pressure, scalar quantity. Pressure is a scalar quantity. Even Young's modulus. Young's modulus is also a scalar quantity. Work or energy, they are all scalar quantities. Work, energy, they are all scalar quantities. There are so many. Okay? Now let's quickly move to vector quantities. What are vector quantities? Vector quantities have both magnitude and direction. They are the quantities that are inherently directional. How do I mean? They are completely described or specified when both their magnitude and direction are provided. And what are the examples of these vector quantities? Examples of vector quantities. We have displacement. We have velocity. We have acceleration. We have force. We have torque. Torque can also be called couple or moment of force. Also call it moment of force. Moment of force. Okay, we have momentum. We have magnetic flux density. Magnetic flux density. We have electric field intensity. Electric field intensity, or what we call what? Potential gradient. We also call it potential gradient. Okay, that will be done later when we get electricity. Okay, and so on and so forth. There are so many normal reaction, upthrust. They are all vector quantities. Okay, we will not be dwelling more on scalar. Our major concern is vector quantities. That is because there are many things that are in vector that we don't need in scalar. For instance, now we don't need a special method to add 2 or more scalar quantities. Like I mentioned 5 kg that time. If I want to add 5 kg to 2 kg, I don't need a special way to add them. But if it's a vector quantity, there are special ways to add them. So we'll be dwelling more on vector. But before we go into that, let's look at how we represent vector. How do we represent vector? So vector representation. Let's look at that. Vector quantities are represented using what we call line segments. Line segments. The magnitude of the line segment, I mean the length of the line segment, show us the magnitude. Okay? And the arrowhead indicates the direction. So a vector quantity is represented by a line segment whose length corresponds to the magnitude of the vector and the direction is indicated by the arrowhead. But in print, in textbooks, in printed materials, how do we represent vector quantities? We use a bold-faced letter. Bold-faced letters are used to represent vector quantities. At times, we use capital letter or small letter with an arrow on top. Capital letter or small letter with an arrow on top. Let's say I have vector A now. This is how I write it, vector A, or I say vector A. Or at times, I write them, I make them very bold. Very bold. So if you open textbooks and you see something like this, they are telling you that A or A, A or A is a vector quantity. So the arrow shows that it's a vector quantity. Alright? Okay? So if I have, for instance now, to write force is equals to MA. I put arrow on this. So that arrow shows that F and A are vector quantities. Okay? Then there's something we call lines, there's something we call line vector. What is a line vector? A line vector is a vector that can slide along any length and still maintain its initial direction. Once direction is maintained, you can call it a line vector. That is where the idea of line segment comes in. Okay? And with the line vector, we can determine that 2 vectors are equal. One example they asked some years back, I think IGM 2016, they asked a question. They said, state 2 conditions for 2 vectors to be equal. 2 vectors will be equal if they have the same magnitude and if they are moving in the same direction. 2 vectors will be equal, or are said to be equal if they have the same magnitude and they are moving in the same direction. For instance now, vector A and vector B, they are equal, provided they have the same magnitude and they are moving in the same direction. But if I have vector A like this and vector B like this, in this case A and B are not equal, even if they have the same magnitude. Why? The direction is different. For them to be equal, vector A, we have to change the direction of one of them. So this minus shows that we've reversed the direction of B. So this is the only way A and B will be equal. When we reverse direction, even though they have the same magnitude. So 2 vectors will be equal if they have the same magnitude and if they are moving in the same direction. Okay? So, bye-bye to that. Let's quickly look at addition and subtraction of factors. Addition and subtraction of factors. How do we add two factors together? How do we subtract two factors? As I have said earlier, we don't need special method to add two scalar quantities together. Okay? But for factor quantities, the direction must be considered. And because of that, there's a special way we add or subtract two factors. But before you go into that, when you add or subtract two factors together, the result you obtain is also called resultant factor. There are various ways to obtain the resultant, but addition and subtraction are just simple ways of obtaining the resultant. We'll go more into that later. So, what is this resultant factor? A resultant factor is that single factor that would have the same effect in magnitude and direction as the original factors are acting together. How do I mean? When two factors are moving in the same direction, to get their resultant, you add them together, and the direction of the resultant will also be in the common direction of the two factors. For instance, let's say we have two people now pushing a car or pushing a load. This is factor A. So the first person, let's say the first person apply 5 Newton force. Second person apply 3 Newton force, and they want to push a car. The total force acting on the car will be 8. So the result will be factor A plus factor B. So to get the resultant now, it will be factor A plus factor B, because the two factors are in the same direction. And whenever two factors are in the same direction, to get the resultant, you add them. You add them. This is opposite to what we call relative velocity. When we get to motion, we'll talk about that later. In relative velocity, reverse is the case. When they're in the same direction, and you want to get relative velocity, you subtract. We'll talk about that later. Okay? So this is 5 Newton plus 3 Newton. And that will give us 8 Newton. As far as factor is concerned, if in theory or in calculation you are asked to do for the result and just stop at 8 Newton, you have half mark. Remember I said factor quantities are inherently directional. They are not complete until we talk about their magnitude and the direction. So in this case now, a complete answer will be with respect to the direction. And what will be the direction? In the common direction of the two factors. In the common direction. Common direction of the two factors. Of the factors A and B. So this is a complete answer now. You've given us the magnitude, you've talked about the direction. So the resultant force acting on the body is 8 Newton. So that 8 Newton will affect the magnitude, will also affect direction. That's why we said the resultant factor will have the same effect in the magnitude and direction as the original factors are acting together. Then what happens when they are in opposite direction? When two factors are traveling in the opposite direction, to get their resultant, the magnitude of the factor, the factor with smaller magnitude is subtracted from that of higher magnitude. And guess what? The direction is always towards the factor with higher magnitude. For example, let's say we have two people. Okay? Let's say we have two people fighting over, let's say, gala. Let's say this is a gala now. Not sausage. Gala is just a sausage. So, one person is holding the sausage here and pulling it towards himself with 5 Newton. The other person pulling it with 3 Newton. 3 Newton. Who do you think will have the gala? Of course, the person that applied the highest force, right? But the resultant force acting on the gala now is not 5 Newton, neither is it 3 Newton, but what? 2 Newton. Why? Out of this person's 5 Newton, he has used 3 Newton to cancel out his opponent's own. So the remaining 2 Newton now is what he will now need to take the gala. Okay, and that's the resultant. So when two vectors are in opposite direction, to get the resultant, you subtract the one with lower magnitude from that of higher magnitude. So our resultant now is vector A minus vector B. That will be 5 Newton minus 3 Newton. And that is 2 Newton. In what direction? You must know the direction. In the direction of A. In the direction of A. That is in the direction of vector with higher magnitude. In the direction of A. The one with higher magnitude. Alright? So, this is how we add or subtract two vectors. The direction must be considered. So, before we say bye-bye to addition and subtraction of vectors, there's another quantity that is similar to this. We call it equilibrant. Equilibrant of two or more forces or vector. Equilibrant. Equilibrant. It's a vector quantity as well. Equilibrant of two or more vector is that single vector that would balance all other vectors taken together. This equilibrant is equal in magnitude to the resultant, but opposite in direction to it. Its own work is just to balance. How do I mean? Let me do the last example here. With this arrangement, 5 Newton here, 3 Newton here, it is obvious that the person that applied 5 Newton will have the sausage, right? But if another person quickly comes and assists him with extra 2 Newton, who do you think they have together? None of them. We have 2 people here, one person applied 2, one person applied 3, pulling the sausage to this side, and we have another person that single-handedly supplied 5 Newton force. Alright? So nobody will have the color because the first total force equal to total force is balanced. So that person with 2 Newton, what he has come to do is to restore balancing. Okay? So the 2 Newton force now that the person applied, the third person applied, is equilibrant. That's what we call equilibrant. And look at equilibrant. Look at the magnitude of the resultant and the equilibrant. Both of them 2. But why resultant acts towards the vector with higher magnitude, equilibrant acts towards the vector with smaller magnitude. So both equilibrant and resultant are equal in magnitude, but they have different direction. They act in different direction. Alright? So let's quickly look at vectors inclined at an angle. Vectors inclined at an angle. Vectors inclined at an angle. Normally, when 2 or more vectors are inclined at an angle to each other, there are various ways to get their resultant. Vectors inclined at an angle. There are various ways to get their resultant. I will just list 6 of them, but the most important one are the first 2. So we have Pythagoras theorem. Pythagoras theorem / trigonometric ratio. Trigonometric ratio. We have parallelogram method. We have triangle method. Triangle method. We have Lamai's theorem. Lamai's theorem. We have polygon method. Polygon method. The one some people also call graphical method. Graphical method. But for today, we're talking about Pythagoras theorem / trigonometric ratio. Another time, we're talking about parallelogram method. Alright? In Pythagoras theorem, we only use Pythagoras theorem to find the resultant of 2 vectors when the 2 vectors are inclined at right angle. Okay? That is at 90 degrees. Remember that Pythagoras theorem states that in a right angle triangle, the square of the hypotenuse is equal to the sum of the squares of the two other sides. And what are these two other sides? The adjacent and the opposite. Okay? So let's say we have vector A and vector B. Vector A and vector B acting at right angle. To get their resultant, you can draw it like this. This is the resultant. Draw a parallel line to vector A. This is the right angle. Then this is the direction of the resultant. At times you can use triangular method. These are the two vectors, vector A and vector B. Then the third side that complete the triangle is the resultant. So Pythagoras theorem and trigonometric ratio are both used when the two vectors act at right angle. Okay? So let's solve examples on this. From Pythagoras now, our R will be equal to magnitude of vector A square of that, square root of A square plus B square, their magnitude. Okay? So let's have an example on that. Let's say a man travels, example 1 now. Let's say a man travels due north. A man travels due north. Covering a distance of 3 kilometers. He then travels due east, covering a distance of 4 kilometers. And God now says, determine his resultant displacement from the starting point. This is a typical question for both WAEC, JAM, NEPO, IGMB, JUPEL. Okay? Let's look at this. This will be the last thing in this video. So solution now. Let's say the man starts from this point A. The question says he travels due north. To cardinal point, we have north, south, east, west. He travels due north means that he just goes north. It goes north, it moves upward. Covering a distance of what? 3 kilometers. 3 kilometers. So to this point B, this is 3 kilometers. So at present, the man is here now. He now said he then travels due east, covering a distance of 4 kilometers. From this place now, he locates east. Where is east? This is north, this is east, this is south, this is west. He travels due east, covering a distance of 4 kilometers. That 4 kilometers will be longer than 3 kilometers. Let me extend it a bit. So this is 4 kilometers. This is point C. So this is where he is now. The answer to determine his resultant displacement from the starting point. So just take your ruler and join this center. That's the resultant. Direction of the resultant will be here. Alpha. So this is right angle. So the original two vectors, 4 kilometers, they are at right angle. So Pythagoras theorem is used here. So from Pythagoras theorem, we have our resultant. Resultant is line AC. That's R square equals opposite. This is OB. Our opposite is the side facing the angle. So that's line BC. Or let me call this one AC first. AC square equals BC square plus AB square. This is Pythagoras theorem. The side facing the right angle is your hypotenuse. So this is our hypotenuse. The side facing the given angle is your opposite. Then the third side becomes your adjacent. So Pythagoras theorem is saying that hypotenuse square, that's line AC, equals opposite square, line BC, plus adjacent square. Our AC is R. BC is 4 and AB is 3. So by the time you find the square root of that, this is 16 plus 9. And that will give you 25. So 25 is 5. So the resultant is 5 kilometers. But for the direction now, that is where trigonometric ratio comes in. So both Pythagoras theorem and trig ratio are used under the same condition. And that is in a right angle triangle. Okay? Now, the question did not say we should look for direction. It only said determine its resultant displacement from the starting point. But remember my definition, vector quantities are inherently directional. Whenever you are dealing with vector quantities, especially in theory, whether you are asked or not, look for a direction. Because it is not complete until both their direction and magnitude are provided. Alright? So for the direction now, that's our alpha. Your direction is always between the resultant and the north, or between the south and the resultant. If by any means your resultant lies between, your direction lies between east and the direction is between east and the resultant, then you have to look for a way of taking it back to the south or to the north. Depending on the condition. I'll give more examples on that maybe another time. Okay? But for this, for the direction now, for the direction alpha, that's where trig comes in. This is opposite, this is adjacent. These are the given two sides. The given two sides. And what connect them from the soccer remember soccer we're talking about sine theta equals opposite by hypotenuse. Adjacent by hypotenuse. Opposite by adjacent. In this case, what connects them? We have opposite, we have adjacent. That's our tour. So tan alpha equals opposite. Our opposite is line BC over adjacent. Adjacent is line AB. So tan alpha now equals BC. BC is 4, AB is 3. And that will give us 1 point. So alpha will be tan inverse of 1.333. So when you press tan inverse, you get 53.1 degrees. 53.1. Okay? Now, that is just angle, not direction. Remember bearing your own level in mathematics. Bearing. We said bearing simply means what? Direction. And we have to talk of bearing. We have what we call cardinal bearing and three-figure bearing. In three-figure bearing, the angles are represented in 3 digits. Even if it is ordinary 5 degrees you want to write, you write it as 005. That's three-figure bearing. But in cardinal bearing, the angles are represented using cardinal points. With respect to the cardinal point, you're the north, south, east, and west. And remember that even there's something we call geopolitical zone in government. No, there are 6. We have northeast, we have southeast, we have southwest, we have northwest, and we have south, and we have north central. So in each case, you see that we make reference to north first or to south first. We make reference to north first or to south first. So the same thing with this. Our alpha now is between north and the resultant, which is a perfect place. So this is north, this is east. So our direction is north, 53.1 degree east. Is between north and east. This is north, this is east. North, 53.1 degree east. This is our direction. Another way of writing this is 53.1 degree east of north. East of north. Nothing like 53. East 53.1 degree north. No, you make reference to north or south first. In my next video, I will give more example on this, because if the alpha happen to be in this place, by the time you get to the 53.1, you have to subtract from 90, because your alpha must be between the north and the resultant, or the south and the resultant. More example next year. Thank you very, very much. If you have not subscribed, please subscribe so that when I upload any other video, you will be notified. Thank you.